This is a revision tutorial for OCR Gateway Physics. We're looking at specific latent heat, which is a section of P1A. So we've talked about raising the temperature of an object. Now we're going to talk about changing state, so melting or boiling. Now to change the state of an object, we need energy. The energy required to melt something or boil something depends on two things. It depends on the mass of the object that you're trying to melt or you're trying to boil, and its specific latent heat. Specific latent heat is a property of the material, and it tells us how easy it is to make that material melt or how easy it is to make it boil. Just like our previous equation, you'll be given this equation in your exam paper. It will be on the inside of the front cover. It will be in this form. You won't be given units, so let's go through those again. Energy, of course, joules. Mass, kilograms, not grams. And specific latent heat, joules per kilogram. We're going to look at an example of applying this equation. So we're going to calculate the energy required to melt 20 grams of ice. The specific latent heat of fusion of ice is 334,000 joules per kilogram. Right, so before we go and look at our equation, one thing that I've noticed is that this question gives us a mass in grams. I know that we always need to use mass in kilograms, so I'm going to have to do some conversion at some point. So now you go to the front of your exam paper and you find the equation that you want. We need an equation that contains energy, specific latent heat, and a mass. And of course we're going to use this one. First thing you do then is write out the equation. Energy is mass times the specific latent heat. And the next thing, we substitute in our values. Now, my mass is given in grams. I actually want it in kilograms. To get my mass from grams into kilograms, I need to divide it by 1,000. I'm multiplying that by the specific latent heat, which is this value up here. And that's 334,000. So 20 divided by 1,000 is actually 0.02, which I'm multiplying by 334,000. We put that into our calculator and we get 6,680 joules. Okay, this next section and the example that we're going to do following this is only for you if you're studying higher tier. Now, if you're studying higher tier, you might get asked to use this equation to calculate something other than the energy. So you might get asked to calculate the mass or the specific latent heat. Again, as I said before, if you're confident with changing the subject of an equation, go ahead and do it. If you're less confident, then use the following method. Now, first of all, we're going to write it into our triangle. Our rule, if there are two things multiplied together in the equation, then they must be multiplied together in the triangle. That means mass and specific latent heat have to go at the bottom. We're left with energy, which is going to go at the top. Now we're going to write two further expressions, one for calculating the mass and one for calculating the specific latent heat. If I want to calculate the mass, I cover up the thing that I'm looking at, I cover up my mass, and I'm left with energy divided by specific latent heat. We can do a similar thing for calculating the specific latent heat. If I cover this one up, then I'm left with energy divided by mass. So I'll write that over here. Specific latent heat is equal to energy divided by mass. Now I have two other forms of the equation that I could use to answer different types of problems. Okay, so this example is also for higher tier only, as it's going to require us to change the subject of the equation. Here we go. 10,000 joules of energy is required to melt a 50-gram wax candle. Calculate the specific latent heat of the wax. Okay, again, before we start, we've got a unit here that we're going to need to change, and that's our 50 grams. We need to have mass in kilograms, so we're going to need to change that at some point. So, first thing I would do is I would go to the front of the exam paper, find the equation that contains energy, mass, and specific latent heat, which is the thing I want to work out. And we should find that the equation is this: energy equals mass times specific latent heat. I'm just using the initials for short. Okay, I'm going to say that I'm not confident with changing the subject of this to give me an equation saying specific latent heat equals. So what I'm going to do is I'm going to use my triangle, and I'm going to put that equation into my triangle. Anything multiplied together in the equation has to be multiplied together in the triangle, which gives me mass and specific latent heat on the bottom. Energy is what's left, so that's going to go at the top. Okay, so now I can use my triangle. The thing I'm trying to find out, specific latent heat, cover that up, and we've got energy divided by mass. So I'm going to write that out here. Specific latent heat equals energy divided by mass. Next thing we do is substitute in the values. The energy is 10,000 joules. The mass is 50 grams. We of course need kilograms and not grams, so I've got to divide that 50 grams by 1,000. Dividing 50 by 1,000 gives me 0.05. Now I can put that into my calculator, and that gives me a value of 200,000. It's a specific latent heat, so my units are joules per kilogram. You will probably be given these units. You are unlikely to have to give them yourself. This graph shows the temperature of a substance as it's being heated. Now we can get a lot from the shape of this graph. If we look at it, we can see that there are some points where the temperature is clearly rising. In this section, and in this section. However, in these two sections here, the temperature is staying the same. This means that in these two sections, despite the fact that the substance is still being heated, it's not actually getting any hotter. So the question is, what is happening to that heat energy? To answer that question, we need to think about the particles inside a substance. Particles have bonds between them holding them together. Now, energy is required if we want to break those bonds. Breaking those bonds in a solid enables it to turn into a liquid, and breaking those bonds in a liquid enables it to become a gas. Now, once a substance is changing state, its temperature doesn't rise. So in these areas here, these sections here on the graph, our substance is changing state. So in this section here, it's turning from a solid into a liquid, and this section here, it's turning from a liquid into a gas. And looking more closely, we can see that those changes of state happen at 0 degrees and 100 degrees. So this is actually a heating curve for water. We say that during these stages, the energy that's being input is being used to break intermolecular bonds. Another way of saying that is that it's being used to break the bonds between molecules. So that keyword there, intermolecular. And that's it for P1A.